So welcome everybody to the last colloquium of the year. And we have the pleasure to host today Professor Ferenc Fodor from the University of Szeged. Professor Fodor graduated PhD in 1999 from Old University. And after some postdoctoral fellowships, he joined the faculty of University of Szeged and János Polgár Institute, where he is now a professor and chair and also head of the institute. And he's a specialist in convex and discrete geometry or discrete geometry, discrete and convex geometry. Sometimes it varies. And we're very happy to hear him speak today about the Lyakhopoulos dual Bolobash-Thomason network.
Thank you very much for the introduction. I'd like to, first of all, thank for the kind invitation. It's very nice to be here. Last weekend, maybe some of you have seen me already at the CMS meeting in Toronto, but today I'll be speaking about something else. So I chose a topic that's probably at least the beginnings of which are familiar to many people, although it doesn't show in the title. So first of all, I'd like to say that this is a joint work with two of my colleagues. One is Károly Böröczky Jr. He's at the Rényi Institute in Budapest, in Hungary, and Pavlos Karantzopoulos, who is a postdoc at the University of Waterloo. One of the occasions, for choosing this topic is just that the paper appeared like maybe 2 weeks ago or something, or 3 weeks ago. Okay, so you can find it actually in the journal Analysis Mathematica. Okay, so the classical Loomis-Whitney inequality, probably many of you know this. I need some notations first. In this talk, E1 through En will always mean the canonical orthonormal basis in Rn. And K in Rn is a compact set. It will always be a compact set. And if the dimension of its affine whole, okay, so this laser doesn't, yes, okay, so maybe I'll use this physical thing, except that I'm left-handed, so I have to reach over. So the dimension of the affine whole is m, then the absolute value sign will always mean m-dimensional Lebesgue measure. So I do not indicate the dimension of the Lebesgue measure. It will be obvious from the context. Okay, so another notation, this piece of E will be the orthogonal projection to Montegro itself. So setting Rn is K such that its affine whole, it's n-dimensional. Its affine whole is full dimensional and it has a positive volume. Then the following is true if you take the projections to the coordinate hyperplanes. This EI perp is the corresponding coordinate hyperplane. So they take the n-1 dimensional volumes of these projections, then this product is at least as large as the n-1st power of the volume. So essentially the idea is that when you take a compact set, a full dimensional compact set with positive volume, you look at its shadows on the coordinate hyperplanes, right? Measure the shadows and try to make some conclusions about the volume of the original set. This will give you, projecting and multiplying them will give you an upper bound. Okay, so that was the classical Loomis-Whitney inequality. And of course, it's not always an equality, obviously, because you can take a brick, right? Just a box, such that, its edges are parallel to the coordinate axes and cut off a corner. Just if you cut off a corner, then projection to the coordinate hyperplanes will not detect this. The projections will still be n-1 dimensional boxes, and their product will be the volume of the box to the n-1st power. Although now that you have cut off the corner, the actual volume of this thing is smaller. So this is not always an equality. It's an equality if and only if this is really equal to a box. Okay, so this Loomis-Whitney inequality has a generalization from the mid-90s. This is called the Bolobash-Thomason inequality, which says the following, a bit of notation. So this n is just a set of first n integers, positive integers. And what we do is we take a subset, sigma, a proper subset, neither empty nor equal to the whole thing, then this E sub sigma is just the linear span of the corresponding basis vectors. So look at the indices of the basis vectors that are in sigma, and then I take the linear span. So this is some sort of a coordinate, not hyperplane, but a coordinate flat, I would say. If you have k of these basis vectors in a particular sigma, and you have a k-dimensional coordinate subspace. So what we do is we take k of these, k such subsets, and we say that this k tuple of subsets forms an S uniform cover for some number S if each number between 1 and n is contained in exactly S of these subsets. So it's a k-fold cover, or sorry, S uniform cover, S-fold cover, whatever. Okay, so the Bolobash-Thomason inequality says essentially the setup is the same as in the Loomis-Whitney inequality. You have k compact set. It's a fine whole, so it's full dimensional. It now doesn't say anything about the volume. It's not necessary. And then you have these sigmas, k of them, that form an S uniform cover for some S. And what you do is you project, but not to the high coordinate hyperplanes, but possibly lower dimensional coordinate subspaces. And here, the absolute value always means the Lebesgue measure in that particular subspace. And so the product is again larger than or equal to k to the power s. This is what you're going to get. Now, in particular, why do I say that this is, although it looks similar, but specifically, if you choose k to be n and s to be n minus 1, then this is just a Loomis-Whitney inequality. So what you do is you take the set from 1 through n, and you're going to have n of these sigmas such that you throw away one of the numbers. And then you get the coordinate hyperplanes. And that's an n minus 1 fold cover. That gives you back the Loomis-Whitney inequality. So this is a kind of a generalization. Now, okay, equality case. One would be interested if this gives you equality, and in what case do you get equality? So if you have such a S uniform cover, then that induces a partition of the set bracket n. In the following way, you take, so this is going to be the partition with sigma 1 tilde, etc., sigma L tilde. So these are non-empty distinct subsets of bracket n, which you produce in this way. So what you do is from each sigma I, you either take sigma I or its complement, and you take the intersection. Okay, maybe some of them are empty, some of them are non-empty, etc. But altogether, the union of these sets will give you the whole bracket n, or the numbers between 1 and n. And obviously, because of the construction, any two of them will be disjoint. So this is something called, this is a one uniform cover. You can say it's an induced one uniform cover of bracket n. And okay, so this is just a disjoint union. And the equality case has been known as folklore. I think it has recently been written down in detail in a paper by Beretsky, Kalantzopoulos, and C in 2023, but this has been around for some time. So, okay, so let me explain. So we have the same setup as before, and this folklore theorem says that you have equality in the Bolobash-Thomason inequality if and only if this K is a direct sum of its projections into these subspaces. But now be careful, because these subspaces into which you project are the subspaces corresponding to this partition induced by the original uniform cover, S uniform cover. So these things could be more than one dimensional. I mean, in the Loomis-Whitney inequality, they were all one dimensional. If you do that equality, like I said, you have an n-1 uniform cover, and it's a little homework to work out that the corresponding partition that it induces is in fact just the n coordinate lines. Okay, so that's this equality case. Okay, now let's look at this from another point of view. These inequalities gave you upper bands. How about lower bands? Can you get lower bands? Well, yes, not by projections, but by intersections. You take sections. So now we're going to look at sections of convex bodies, or well, sections of things. Here they're going to be convex bodies. The conditions are slightly different. Okay, so this is due to Mayer from 1988. The setup is that you have a compact convex set in Rn such that the origin is in the interior. Obviously, that's needed now because I want to intersect it with hyperplanes, linear, or subspaces. Here they're going to be coordinate hyperplanes. And so what we do is now we intersect this body with each coordinate hyperplane, take the corresponding volume of the intersection, multiply, and what we're going to get is a lower band modulo some constant, depending on the dimension. We're going to get a lower band on the n minus first power of the volume. So this sort of, I would say, Loomis-Whitney and Mayer, sandwich the volume from above and from below. And here the equality case is also known. There is equality exactly if K is the convex whole of, again, these are segments. So this is pretty much like a distorted cross polytope, if one looks at it that way. It's not really a regular thing. These lambdas are positives, and so these are just segments centered at the origin. Take this convex whole. So it's like a cross polytope. Okay. One thing is you have to observe that unlike in the case of the Loomis-Whitney inequality, here you need that in order to make a meaningful statement, you need that K is convex. Otherwise, the volume of K can be arbitrarily small, even if the sections are large. So then that wouldn't make sense. Now, I don't want to give, this has been around this topic for a long time. There has been much work done. Many people worked on it. There are many different results, generalizations, etc. I do not want to give an overview because that would take up the rest of this talk. I just mentioned a few names who actually proved similar various reverse and dual Loomis-Whitney type inequalities. But there are many more, and I'm sorry if I missed somebody. I don't want to talk about that more. Okay, so now I want to explain the title of the talk. We haven't got to the title yet. Well, part of the title was Bolobash. I have already told you, but there was no Liakopoulos. Okay, I need a bit of preparation for that. So what I'm going to say is that when I have in Rn these non-trivial subspaces E1 through AK, and some positive constants C1 through CK, they are said to form a geometric Bruskamp-Leib datum. If the following is true, if this weighted projection, if you weight the projections with the CI and add them up, then this is just the identity map on Rn. This is like a decomposition of the identity in a way. Okay, so this was called the geometric Bruskamp-Leib datum in a paper by Bennett, Carberry, Christ, and Terence Stowe. In particular, just to give you an example of such an animal, is that in the Bolobash-Thomason theorem, when you have an S-uniform cover with these coordinate things, then that's a Bruskamp-Leib datum actually with Ci all equal to 1 over S. That's one of the easy examples. Okay, so how about this word? This name that was in the title. So now I have come to the point where all the title is explained, more or less. So the following theorem was proved in 2019. This is a generalization of Mayer's theorem, similar in flavor as the Bolobash-Thomason theorem was a generalization of Loomis-Whitney, but it even goes further. Okay, what it says is the following. So K is again in Rn a compact convex set. Origin is in the interior. And now you have these linear subspaces E1 through EK and corresponding real numbers such that they form a geometric Bruskamp-Leib datum. The dimension of EI is equal to NI, just I need the notation. Then you get the following lower band for the volume. This looks pretty much like Myers inequality. Here you have intersection volumes, but they are raised to the Cth power, so they have some exponents. And then there is a fancier constant, in a sense. So it's a kind of a bit fancier. Now, what's the major difference? The major difference here is that we forget about coordinate hyperplanes. There are no coordinate hyperplanes anymore. So now we are looking at a general system, in some sense, a general system of linear subspaces, not just coordinate hyperplanes and smaller dimensional coordinate subspaces, etc. But we let the subspaces loose. The only condition is that they form this geometric Bruskamp-Leib datum. So in a sense, they form a decomposition of the identity. Okay. Here also convexity is a necessary condition for the same reason. If it's not convex, the body, then you can have arbitrarily small volumes, even if the section volumes are large. Okay, now, in order to describe the equality case, I need more terminology. When you have a Bruskamp-Leib datum, E1 through EK with the corresponding constants, then introduces this goes back to the 2000s, was introduced by Valdimarsson, who actually proved the equality cases of the geometric Bruskamp-Leib inequality, and I'll get to that in a minute. So I need the notion of independent subspaces. So what you do is you take these E1 through EK and do the same thing as we did with moving from an S-uniform cover to the induced partition of the set 1 over n, which means that you take an intersection of k things, and in each thing, you either have the subspace or its orthogonal complement. Right? It's 2 to the k. Animals, some of them are empty. Yes, well, I mean, not empty, but trivial, contain only the zero vector. That could happen easily. And if such a thing it's a proper subspace, in the sense that its dimension is at least 1, it's called an independent subspace. So these are the independent subspaces. Actually, a funny thing is that independent subspaces may not exist for all Bruskamp-Leib data. One can come up with examples where that's the case. For example, in joint decomposition of the identity, you run into trouble. But I don't want to go down that road. Okay, so now I can give you a characterization of Yakupoulos inequality. So we have equality in Yakupoulos inequality if and only if these independent subspaces, these FJs, F1, F2, etc., FL, associated to a Bruskamp-Leib data, span Rn. Obviously, if they exist, I mean, if you have 2 of these independent subspaces, then they are orthogonal to each other. That's by the definition. And they may or may not span Rn. There are cases when they do not span Rn. There are cases when even there are no independent subspaces. But this says that you can only have equality in the Yakupoulos inequality if these things actually span Rn. That's one thing. And K is equal to the convex Hall of the intersection with these independent subspaces. So what you do is you take the intersection with each independent subspace, you get some lower dimensional object, and then take the convex Hall of their union. Okay, so it's in the special case when actually it's not just the Bruskamp-Leib datum, but these are coordinate hyperplanes. The equality was proved already by Beretsky, Kalantzopoulos, and Xi in 2023, but that's a very special case. Okay, so what are the tools? Well, originally, The Loomis-Whitney inequality was proved by different means. The modern proof usually uses the geometric Bruscamp-Leib inequality, which is just essentially one or two lines. Very simple. And okay, so the geometric Bruscamp-Leib inequality says that, again, you have the same type of geometric Bruscamp-Leib datum that explains the name. And you have these non-negative L1 functions, the Fi. Then the left-hand side, which is, evaluate the Fi at the projections to the EI, take multiply them. The integral of this is less than or equal to the right-hand side. This is a well-known inequality in analysis. It's called geometric. This is not the most general form, of course, of the Bruscamp-Leib inequality. It's called geometric because here inside you have an actual projection. This is because of the projection. Normally, in the general Bruscamp-Leib inequality, this is just a surjective, some surjective linear map. It doesn't have to be a projection. But here, this is an orthogonal projection. So that's why it's geometric. That's the geometry behind it, whatever. I mean, this is how it's called. Again, simple homework. In the special case, when all these EIs are equal to whole Rn, and then the CIs add up to 1, then you just get Beck-Hölder's inequality. So this is a finer tool than Hölder's inequality in a sense. Okay, there's a long story, how this was, investigated. I do not want to give an overview of that. In particular, I just want to say that the Bolobash-Thomason theorem, which also implies the Loomis-Whitney inequality, can be easily proved using the Bruscamp-Leib inequality by choosing the EIs to be these E sigma-Is, the corresponding constant by 1 over S, and then you just use it for indicator functions. It's literally 2 lines. I'm going to show you a proof using something like this, but not this particular one. Okay, the question, so how do you get the equality case? Okay, this will give you an inequality, but in order to get equality, you have to know the equality case in the Bruscamp-Leib, in the geometric Bruscamp-Leib inequality, right? If you are using that. And that's a difficult question. In particular, if these Fi's are, identical Gaussians, then you always get equality. But that's not the only case when you get equality. So there was a long history of the investigation of the equality case, and I think in 2008, Waldy-Marson was the one who actually characterized equality, in full precision. And I show you that on the slides. So I say the equality case, the idea of a critical subspace. So again, we have this Bruscamp-Leib data, and V subspace is the non-zero linear subspace is critical if it has this decomposition property. I'm not going to be using it very much in this talk, but it's in the statements. Okay, as I mentioned already before, that if you have 2 independent subspaces, then they are orthogonal to each other. So then one is in the orthogonal complement of the other. Okay, so now let F1 through FL be the independent subspaces associated with the particular Bruscamp-Leib datum. As I said, these are pairwise orthogonal subspaces that may or may not span the whole space. So what we do is we define the dependent subspace associated with this Bruscamp-Leib datum, as the orthogonal complement of the direct sum of the independent subspaces. This may be empty. It may be trivial. It can easily happen that it's trivial. So in this case, Rn decomposes into direct sum of the dependent and the independent subspaces. Okay, so now here's the theorem of Waldy-Marson. Sorry for it's a mouthful. This is the equality case. Luckily, I had to need some one slide, but I try to explain. I'm not going to explain the details. It's not that important because I won't be using it. Just the phenomena The beginning is just, it states the conditions. You have a Bruscan-Leib datum, you have dependent and independent subspaces, etc. And what it says that if you have equality in the geometric Bruscan-Leib inequality, then each function should look something like this formula. And what does this formula include? Well, there is this exponential part. This looks like a Gaussian type thing. And then there's this product of a bunch of functions. How many functions? Well, independent subspaces, live in these EIs somewhere. That's how they were created. A single EI may contain a bunch of these independent subspaces. And so each Fi in the Bruscan-Leib and geometric Bruscan-Leib inequality will have this exponential, and then it will have this product of, well, as many functions as the number of independent subspaces living in the EI. And what it says is that essentially these HJs, these functions, can be chosen arbitrarily. These are totally arbitrary. There's no condition on those. So it says that then there exists a B, dependent subspace, some positive constants, and K, non-negative integrable functions, if the number of such FJs is K, and a positive definite matrix acting on the dependent subspace such that its eigenspaces are all critical subspaces. And so the function is like this. And essentially here, it tells you what the thing is. It's quite fixed. So there exists an A and there exists a B. And that tells you that this exponential part, what it is. But it doesn't really tell you what this, this tail is, the product. You can choose those HJs to be anything. And that's why they are called, those subspaces are called independent. Because these are totally independent from the whole thing. And if your functions look like this, then you have equality. So this is if and only if. Okay, so this explains the term of the independent subspaces. That's one thing. In general, okay, so critical subspaces, all independent and dependent subspaces those are critical subspaces, but there may be more critical subspaces. So, but like I said, I mean, we don't go down that road. Okay, so next, but this was used can be used for the Loomis-Whitney and the Bolobash-Thomason theorem proof, and including the equality case. So how about Myers and Yakopoulos? There you need the reverse form of the geometric Bruscan-Leib inequality due to Frank-Barth. Okay, so now I'm going to be using this integral with a star to denote the outer integral for, well, possibly non-integrable function, non-negative function. And this is the theorem. You see, on the right-hand side, you have the same stuff as on the right-hand side of the Bruscan-Leib inequality, except now the inequality sign is reversed. Now, this is going to be a lower bound for the following integral. Here, what you do is, in the function, in the integral, you take the supremum, you take the decomposition of this x. So we take the x, we're integrating with respect to x. Take the decomposition of this x in every possible way, such that it's x equals this, ci times ci xi, the sum of this ci xi. So the xi all live in these subspaces ei. This is usually not unique, obviously. There are many ways of doing this. So what you take is take the supremum and integrate. Now, this may not be an integrable function, obviously. I mean, the supremum, you don't know. So therefore, this is an outer integral on the left-hand side, in case this is not Lebesgue integrable. And so this is a lower bound. Then the right-hand side of the geometric Bruscan-Leib inequality acts like a lower bound. Again, this reduces to one of the well-known inequalities in the special case when you choose in the Bruscan-Leib data A1 through AK to be the whole space. Then you get the Plakoff-Aligned inequality, if somebody knows that. It has actually some connections to Szeged. These were two Hungarian guys. This guy Leindler was a professor at Szeged, at the same place where I am. I don't know if you know it, actually, the Riesz representation theorem everybody knows. Friedrich Ries was a professor at our institute in Szeged. He was actually serving as the president of the university for some time. Also, everybody knows Haar measure. Alfred Haar was a professor at our institute. So, okay, I don't want to explain the Praecopa-Lindler inequality in detail, although I have a few slides. This is a special case. It's stated as a special case of the reverse Bruskamp-Leib inequality in this form. This is not the most common form that you will find in literature, but this is the one that actually one needs in these arguments. So this is just specialized when the EI equal to Rn. And those of you who know the Brun-Minkowski inequality and convex geometry, then you may know that this is a functional form of the Brun-Minkowski inequality. So it has some geometric significance as well. Now the point is that in the equality case, naturally log concave functions show up. This is an important thing. So this is just a definition of a log concave function. It really says that it's the e to the negative phi, where phi is a convex function. And okay, there are a few properties of log concave functions. I skip over that. So here's the equality case of the Praecopa-Lindler. It says essentially that in order to have equality, you have to have these constants and these vectors and the log concave function phi such that this weighted sum, so the centroid of this vector system with these coefficients is the origin, and then the Fi are all equal, like this. So log concave functions in the extremizers naturally show up. So this explains in a sense that if you look at the equality case in Frank-Barth's reverse geometric Bruskamp-Leib inequality, as the special case is the Praecopa-Lindler, so you expect that somehow log concave functions will pop up. This is even longer than the equality case of the geometric Bruskamp-Leib. I just want to point out the differences, okay? Just a few differences. The statement looks very similar. You have this, function here. Again, it has an exponential part. It's kind of the Gaussian part, and then you have these products. The products are also over the independent subspaces. So here again, these HJs are the kind of arbitrary functions. But now these translations that are in the functions could be different for each function. Before, in the geometric Bruskamp-Leib, you had the same translation for each. Now it splits. So you have these BIs. That's the same I as the I in the FI's index. And also you have these WIs that live in EI, these translations. But other than that, it looks very similar. Okay, so the theta are positive, the BIs are in EI intersection with the dependent subspace, the WIs are in the EIs. The HJs are non-negative, and under certain conditions, not always actually, under certain conditions, they are not just any functions. Here there is one condition. If this is satisfied, then they have to be log concave. So it's not completely free anymore. And A is a positive definite matrix, again, with eigenspaces, critical subspaces. And it works vice versa. If your functions look like this, then you have inequality. Okay, so now let me tell you the sketch, the original proof of Yakopoulos, and I'll indicate how equality case works. And so you're going to see a proof with the reverse Bruskamp-Leib inequality. The idea is to choose the right functions. That's the art of it. In general, if you want to use indicator function. It's simple enough. But here, no. Here I have to use this gauge function first. Okay, so if for a vector x in Rn, define the k norm or k gauge of x as the infimum of all non-negative lambda such that x is in lambda times k. It's called the gauge function. Consider f of x, which is just the exponential of the gauge function. It's a Minkowski functional or Minkowski function associated with k. Okay, so this is obviously a log concave function because the gauge function is convex. And also at 0, its value is equal to 1. Okay, it is also known in geometry that if you integrate this Minkowski function over Rn, then essentially what you get is the volume of K multiplied by n factorial. It's a constant depending only on the dimension. This is elementary convexity. Okay, so now how are we going to use this? We're going to use it the following way. First, just take the nth power of f, that's just the nth power, and integrate it over Rn. What happens if you do that? Well, I mean, if I want to use Bruskamp-Leib or reverse Bruskamp-Leib, then I would have to have a product of functions. So I'm going to produce a product of functions and I'll raise this function to the nth power. Okay, so what happens on the one hand if you integrate this? Well, okay, this is just integral of e to the negative n times the k norm of y dy, which is the same thing as you integrate e to the negative y, but now you take this norm with respect to 1 over n times k, right? Homogeneity. And so according to the above formula, this will be the volume of 1 over n times k times n factorial. And the volume, of course, of 1 over n times k is 1 over n to the n times the volume of k. So essentially, when you take the nth power and integrate it over Rn, then again, you get the volume of k with a different constant. Okay, so now I claim the following, that if you multiply this stuff with n to the power n, then it will be greater than or equal to this on the right-hand side. That looks very much like what you have in the Bruskamp-Leib and reverse Bruskamp-Leib inequalities. Okay, so I'll prove that. Okay, so take a z. This is a vectoring space, and decompose it in this form, sum of ci times xi, such that the xi are from the subspaces ei. This is possible in many different ways. We just take one. Okay, now consider f of z over n. Okay, well, write in place of z, write this sum. And so that the ci appears, the xi appear, and there's the n. And I multiply and divide it by n sub I. N sub I is the dimension of ei. Why do I do that? Well, because if you look at the separated coefficients, the sum of these separated coefficients is equal to 1. You can see that because in the Bruskamp-Leib data, you have a decomposition of the identity. And if you equate traces on the two sides, you're going to see that the sum of these things is just equal to 1. So really what you have here, in a sense, is a convex combination. This is a convex combination, and you can use the log concavity of the function to lower band it. And the lower band is this on the right-hand side. Of course, here you have the ni here, the ni there. But if you recall what the definition of f is, then that just disappears, because this is e to the 1 over ni xi norm with respect to k. And this is raised to the nth power so that the ni just cancels out. So you get that stuff on the right-hand side. Okay, now, so which means that f of z over n is greater than or equal to this product for any choice of decomposition. It doesn't matter. We took an arbitrary decomposition. Okay, so now integrate the left-hand side, integrate. And on the right-hand side, we're not integrating this, but the supremum over all decompositions. Well, take the outer integral. Of course, this is integrable, so it's equal to the outer integral. Outer integral is still monotone. And then you have this inequality. So you get that inequality. And the second inequality is just the reverse Bruskamp-Leib inequality. This is just the reverse Bruskamp-Leib inequality. So left-hand side, compare right-hand side. We are almost there because the stuff in the box was almost like that. But on the left-hand side, we had something different, slightly different. First of all, I had to the n to the nth power, and then I had integral of f of y to the n. But that can easily be fixed because make the change of the variables on the left-hand side. use y equals z over n. And naturally, the n to the power n will appear as a factor, right? Just, rabbit out of the hat. And so if you do that, then you just get that inequality that was in the box. Okay. Okay, so now how to get Jakopoulos inequality from this? Very simple. The left-hand side, if you look at it, okay, so remember the left-hand side. And when you look at the left-hand side, we know exactly what this is because it was calculated before, right? The integral of the nth power of this function, this integral is known. It's the volume of k multiplied by this thing. N to the power n cancels out. So this is just n factorial. The left-hand side is just n factorial times the volume of k. Okay, what's the right-hand side? I evaluate the right-hand side. So here the fi are, these are, nothing else but f restricted to the subspace ei. So it's still the Minkowski function, that stuff. And what you're looking at is you're only working in this subspace ei. And then you only need to look at this norm, or, well, the gauge with respect to the k intersection ei, right? Because everything lives in ei. Things outside ei do not really matter in the value of this gauge function. And okay, and again, use the formula that this is going to be just the volume, ni-dimensional volume of k intersection ei multiplied with this ni factorial. And then when you compare the two sides, you get the statement. So this is the proof, the short proof of Jakopoulos theorem, modulo some minor details. Okay, so how is equality? How do you get equality from this? Well, if you want to get equality, then we had two inequalities. Let me just scroll back quickly. Here. This was the key, essentially, to proving Jakopoulos inequality, because we calculated this, that's an equality. We calculated that, that's also an equality. So in order to have equality, you have equality here and equality there at the same time. One is you have to have equality in the reverse Braskamp-Leib inequality, that big ugly theorem. And you also have to have inequality in this, essentially in this stuff in the box. Well, here on the left-hand side, sorry, here. Both places. And have to be satisfied at the same time. Okay, so how does that work? Okay, let me check what the time is. Okay, I still have time. I think I used up 44 minutes and 36 seconds. So, okay. So if equality holds in Jakopoulos, then okay. So first of all, you're gonna have equality in the place where we used the reverse Braskamp-Leib inequality. Okay, since each fi is log concave, and the support of each fi is the full space ei, it follows that the functions should look like this. This is sort of reduced compared to that theorem, the original theorem. This is where I don't want to check all the details. So, but the difference is here that it is essentially what's in the theorem, with the exception that there is no translation here and no vector here. One has to check that, but that would take more time than I have. Okay, so if you look at the equality case in the reverse Braskamp-Leib inequality and look at it in this particular special case when these FIs are log concave, at 0 their values are equal to 1, they have a unique maximum at that point, etc. That sets extra conditions on the extremizers, and then turns out that these translations disappear. Okay, and so we have these thetas, that's a positive number. In this case, one can assume also that the Hj, is log concave. That was in the theorem. And the A is still, this capital A is still a positive definite matrix, such eigenspaces are critical subspaces. Okay, so a somewhat simplified functions. And don't forget that on the left-hand side, in the guise of fi of x, that's the Minkowski function. That's a Minkowski function, well, restricted to the subspace ei, which tells you the shape of the convex body. So this essentially tells you something about the shape. This is what we're going to use. Okay. Okay, so Fi have a unique maximum at 0, which equals 1. We may assume that these Hj's also have a unique maximum at 0, which is also equal to 1. No difficult to see, and we can also, since they are local, we can assume that each Hj is in this form e to the negative phi j for some convex function phi j, such that phi j of we have to have one. So now I modify the formula like that. The only modification now is that instead of, if you look at the previous slide, instead of the Hj's, I have the e to the negative phi j because of the concavity. Okay, so if now you recall that what the Fi of x stands for, that's e to the negative 1 times the gauge of x. So on both sides, you have exponentials, take the logarithm. If you take the logarithm, then on the left-hand side, you're going to have the gauge of k. And on the right-hand side, you're going to get that exponent and that the sum of those exponents. Of course, you know, the minus sign disappeared from everywhere. Get a minus sign everywhere. So this is a formula for the gauge function that tells you the shape quite directly. Okay. Now, the first thing I want to show that this first term here is 0. That's not there. That's the first thing. Okay, so I claim that in this particular case, when you have equality, there is no dependent subspace. So the dependent subspace is trivial. Okay, that's the first thing. If you remember, maybe I'll scroll back later just to recall what the statement was about the equality case. The equality case started, the theorem started like independent subspaces span the whole Rn, which means that since the dependent subspace is the orthogonal complement of the sum of the dependent subspaces, therefore it has to be the trivial subspace. So that's the first step. Okay, how do you do that? This is a funny one. Suppose indirectly that the dependent subspace is non-trivial, its dimension is at least 1. It's a contradiction. Since each EI can be decomposed in a way, well, you can decompose it in a sense that use dependent and independent subspaces, right? The Rn is the direct product, direct sum, and EI is a critical subspace. So you have this decomposition, which means actually that if you only take projections onto the intersections of the dependent subspace and EI for all I, then what you're going to get, because of the Bruscombe condition, this is going to be the identity. This is the decomposition of the identity. This is just a restriction in that sense. It has to be the identity on the dependent subspace. Well, obviously, the dependent subspace has to intersect one of the EIs, because if all the intersections are trivial, then this map will be trivial, right? And it cannot be the identity on an at least one-dimensional subspace. So you have to have a non-empty intersection. So there has to exist some EI such that EI intersects the dependent subspace. Take a point from it, an arbitrary point, x0. Pick your favorite point. That's not the origin. Okay, origin is disqualified. Okay, so now if you look at it, let's see, where was that? I'm going back to the formula. Yeah, here to this formula. Remember this formula for a second. So apply that to, let's see, to x0. What happens is you take the projection of x0 to fj, then you get 0. It's always 0. Why? Well, because x0 is in the independent subspace. That's orthogonal to all of the dependent subspaces. So if you project it to an orthogonal, a subspace orthogonal to it, then you got you got 0. Okay, so then take the k norm of t times x0, okay, and divided by t squared. This is, again, rabbit or out of the hat. And let t go to infinity. Obviously, the limit will be 0, right? You have t on the top and t squared at the bottom. How does it gonna give you contradiction? Well, okay, now apply this formula that I said, this one, see what happens. Okay, so if you plug in x naught into here, then these projections are gonna be all the origin. That's all 0. So this thing disappears. That's just 0. So the only thing that you have is this part, the first part, nothing else. Okay, and then what does it look like? Well, A applied to Tx naught, but of course in the formula itself there's a projection to the dependent subspace, but x naught lives in the dependent subspace, so for it, it's just the identity. So it turns out that this will be A applied to Tx naught, scalar product Tx naught. You see, you have the t there and the t there. T squared. So the t cancels out. And what you have is A x naught, x naught. And since A is a positive definite matrix, this has to be positive. On the other hand, this limit is 0. Contradiction. So you have we proved the claim. Dependent subspace is trivial. Okay, looking at the time, I still have some time. So it turns out that independent subspaces span whole Rn. And then when you look at this formula for the k norm of x, then that first term disappeared. Now you only have the sum of these phi j's. Okay, next, in order to verify the important part of this thing, or well, let's say the second thing, what does k look like? Now, okay, what we're going to do is the following. One thing is, you notice that if you have a point in one of these independent subspaces, then if you project it to any other independent subspace, you get the 0 vector, and the value of the 0 vector is 0. That's what we agreed on. So therefore, when you take a point, it decomposes actually. So if your point is in Fm, right, in this index M independent subspace, then in this sum, in this sum here, all terms will be 0 except the one that corresponds to Fm. Right. But then there's nothing else on the right-hand side, so phi m of x will be equal to the norm of x. With respect to, when you restrict k to this subspace. So that's the funny thing. And of course, you can, when you have a point in EI, then the independent subspace is also span EI. And so you can actually project to each one and add these up. Right, so your point is in one of these FJs, just one of them. For all the others, it will be 0. So if I write it as a sum like this, I do not really cheat. Depending on which FJ your x is in, different one of these terms will be non-zero, but only one of them, and all others will be 0. And I can even extend this to all. This was only for independent subspaces that live in EI, but actually I can extend this, why not, for all independent subspaces, because they are all orthogonal. They would still be true, because take a point in Fm, and the projection to any other independent subspace will be the 0 vector. So in fact, the norm of x will be equal to the sum from J1 equals 1 to L, these norms. Okay, that's one thing. Okay, so now consider another convex body. So take the intersection of K with these independent subspaces and take the convex hull of the union. We claim that in the equality case, it has to look like this. Okay, on the one hand, Well, it's just an application of the previous formula. If you take somebody, the norm or the gauge of Z with respect to M, then it will be the sum of the norms of the projections with respect to K from J equals 1 to L. This is because of the decomposition, this orthogonal decomposition. And anyways, when you have an orthogonal decomposition and you take a vector, then you can, this is a simple thing that maybe I leave as a homework. Then what you can do is you can calculate the gauge such that you take the projections of the vector into these, pairwise orthogonal subspaces, and then calculate the gauge with respect to the intersection of that subspace with K, and then add them up. So this is just the property of the gauge function. On the one hand, M is contained in K, obviously, because we take intersections of K with subspaces. Those are inside K. And we take the convex pole, that's still inside K. So M is a subset of K, therefore, its gauge function is larger than or equal to than the gauge function of K. This is monotone, reverse monotone. Now we just have to actually show the opposite inequality, and then we are ready. So two gauge functions are the convex one is very equal, but is very equal. We worked on the parts where we use the reverse Bruscombe-Leib, but we have already forgotten about the other inequality. Now here it comes to play. So there was the two inequalities where e to the, well, on the left-hand side, there was this f z power n greater than or equal to the supremum of whatever thing. Now, this is an equality. Okay, so we have an equality, which can be rewritten in the following way. Take these are all exponentials on both sides. Take the logarithm. On the left-hand side, you have z, the K gauge of z. On the right-hand side, because of the minus sign, you're going to get, instead of a supremum, you get an infimum over all decompositions of z in this form with the xi's, the xi living in ei. But really, the ci don't really matter here, in a sense. They can be absorbed and call the new vector as a yi. So really what we do is you decompose z into the sums of the yi's. The yi's live in ei. Okay, so this is an equality. Okay, so here, this is an infimum. Okay, so this is an infimum, which means that the K gauge of z equals the infimum of this sum here over all decompositions. But if one takes a closer look, it's not difficult to see by a compactness argument that actually this is a minimum, not just an infimum. So it's actually attained. So by a compactness argument, actually there do exist yi's, so yi in ei, such that z is actually equal to this thing, and the K gauge of z equals this sum. And we are almost ready. This is the last equality when putting everything together. So on the one hand, if I don't mess it up, then all these sums and decompositions. So start with the K gauge of z. On the one hand, take this decomposition that we agreed it exists by compactness into the sum of the yi's. So essentially this equality is just copied here. Okay, the next step, we agreed before that for each vector in space, the K gauge can be produced as a sum of the K gauges of the projections of this vector onto the independent subspaces and add them up. The next step is just switch the order of summation. There's nothing fancy about that. And then use the triangle inequality. So that inequality is just a triangle inequality. So there's nothing fancy going. Triangle inequality. Okay. And then again, when you look at this thing, then since you know that this will be only zero, only non-zero for certain j's, it will be equal to that sum. And in the end, if we jump back, that equality is this. So maybe I should have color coded the equalities, or indicate in which step which one to use. It's kind of easy to forget once you get there. So what does it mean in the end? It means that the k gauge of z is greater than or equal to the m gauge of z. So since the opposite inequality automatically holds, because m is a subset of k, we have equality. And that's it. That's the proof. And that pretty much ends the talk. There's one thing I want to say here. I see. Okay, I'm over 1 minute, but we had some trouble here with the technology. So let me just say that what is the next step? The next step would be a stability statement. Now we know exact conditions for the equality case. One would need a stability statement. What's the difficulty with that? Well, you need, at least for certain restricted class of functions, the stability of the reverse Brusc-Complete inequality. Which has been done before for special classes in the proof of other inequalities. But what's the difference here is that here you have, in those cases when previously the stability was shown for certain classes, these subspaces were all one-dimensional. But here, these are not one-dimensional anymore. So probably some new ideas are needed. So those techniques that have been used for the stability of the reverse isoperimetric inequality and etc. Will not automatically work here, because here these Brusc-Complete data is more complicated. You have possibly higher dimensional subspaces, and that causes certain complications. So, but that's the next step. And so thank you very much for your attention.
So this proofs, they depend heavily on the Euclidean structure.
Yes.
But there is a Brusc-Complete two actually, at least for the sphere.
Yes. Not that I know of. This is very new. I mean, the paper appeared recently, but we just submitted it in the summer. So this is a really new result. We haven't thought about anything else. We actually started to think about or planning to start to think about the stability. So we moved into the direction of the stability. But yes, thank you. That's actually a meaningful point. Yes. Yeah.
Freezing here, so I think we should save the speaker again and move on to the